Hello AP Chemistry and welcome to Buffered Solution 17.2. So here is where here is where we take everything from the last chapter and wrap it up differently, right? We're going to wrap it up and talk about buffers. So first let's talk about what is a buffer, right? So first of all, obviously there's the simple definition, right? A buffer is a solution that resists changes in pH, right? That would be thing number one, right? So we resist changes in pH. And then let's talk about what is a buffer in terms of what is it made of, right? So we have acidic buffer, right? And in order to have an acidic buffer, that means we're going to have a pH of what? Right, less than 7, right? So for an acidic buffer, we're going to be talking about a weak acid and its conjugate base. For a basic buffer, meaning pHs of, right, above 7 up to 14, we're going to be talking about a weak base and its conjugate acid, right? And it has to be those pairs, right? And if it's not those pairs, it's not going to work. So if you're presented a question wherein we have hydrochloric acid and its conjugate base, which is, right, chloride ion, if we're presented this as an option for a buffer system, the answer is, right, no, it's not a buffer because it doesn't meet these criteria, right? Must be a weak acid and its conjugate base for an acidic buffer, or a weak base and its conjugate acid for a basic buffer, right? There are no exceptions to that. All right. So let's talk about why that's the case, like why those things make up our buffer systems, right? So here we have our general dissociation or hydrolysis reaction with water for a weak acid. We're going to call this our weak acid, right? And this over here is its conjugate base, right? So let's talk about writing a K expression. This would be a K what? Right, a Ka, and it's going to be hydronium ion, A minus ion over Ha. That's my Ka expression, right? Now, if I were to rearrange that just a little bit, right, I can rearrange it so that way it says Ka times Ha over A minus gives me H3O plus. Yes? So all we did was rearrange it, right? We brought that up, brought that down, and it gives us this version of it, right? Note that this is what the Henderson-Hasselbalch equation is based on, okay? So your book talks about, I don't know, for about a page or something, talks about the Henderson-Hasselbalch equation, right, and its usefulness. Note that it only applies to buffers, only applies to buffers. So if you want to memorize it, that's great, it's awesome, and it can be helpful sometimes, right? But note that you don't need it, right? It's not going to, there's nothing that you would use that for that this doesn't get to in the exact same way, all right? So now if we look here, right, we know that H3O, which is the thing that determines pH, is equal to this relationship, right, where we have our Ka, we also have our Ha over our A minus, right, where Ha is my weak acid, this is its conjugate base, right? Note that if we go back one slide, that's what we were talking about, right? An acidic buffer is composed of those two components, right? So we got that here. And then we have our Ka value. Now, couple of notes here, right? So if we have both of these in solution, let's go forward a slide. So here we have a weak acid, right? And its conjugate base. So it turns out when I have both of those species in solution, right, and this is why it has to be a weak acid, because we know that if we have a weak acid, its anion is also a weak base, right? Meaning that if we were to put actual identities here, right, if we were to talk about fluoride ion, right, fluoride ion does have a tendency in water to do that, yes, right? Likewise, HF in water does have a tendency to do this, right? Both of these reactions are a possibility, right, when I have both of these species present, right? Which is what this diagram is talking about, right? It says that as long as we have both of these species present, if I were to add some base, it's going to neutralize some of that acid, right? So it's going to decrease by X the amount of acid, increase by X, right, the amount of fluoride ion. Yes, does that make sense? If we come over here, if we were to add strong acid, right, we are going to neutralize some of this base, right? So we're going to lose some of that, and we're going to produce some of that. Yes, does that make sense? So if I think over here, right, If I consume some of my HF, I'm going to produce F minus. If I consume some of my F minus, I'm going to produce HF. Yes? Does that make sense? Right? Those are just the chemical reactions. All right. So if I look here, right, what that means, right? A couple of important notes in terms of buffer properties, I guess. Okay. So first of all, we have our buffer range. Okay. Our buffer range, one of those keywords. And our range is always going to be what? Right. Plus or minus 1 pH unit from pKa. All right. Now, let's talk about why that's the case, right? Because pH is based on this, right? And pKa would be the negative log of Ka, right? Which means that if we look here, if these are equal, right, then Ka is equal to H3O plus, yes? If HA and A minus are equal, Ka is equal to H3O plus, right? Which means that my hydronium ion concentration in buffer system is absolutely dependent on my Ka value. So the closer that these two are, the better my buffer is going to be, right? Which is why the range is, the effective range of a buffer is plus or minus 1 pH unit from your pKa, all right? So for example, if something has a pKa of -4, right, or if something has a pKa of 4, it's going to be a good acidic buffer from a range of what? Right, a range of 3 to 5, okay? And that's my pH, my buffer range. Now, my buffer capacity has to do with these two concentrations here, right? How big are these two concentrations? Capacity is simply what the word implies, right? How much can it neutralize without a significant change in pH, right? So once we fix this, right, and this is close to my desired H3O plus concentration, these two things then determine our pH, right? Again, please pay attention, right? When these are equal, Ka is equal to H3O plus, all right? Now, let's say that these are 2 molar each, right? 2 molar and 2 molar, right? That means this ratio changes very, very little if I add a tiny amount of acid or base, right? So for example, let's say it became 1.8 over 2.2, right? That ratio doesn't change significantly, right? And as long as this ratio doesn't change significantly, neither does my pH. Yes? Does that make sense? Okay. And that's my buffer capacity, because if something is 2 molar versus 2 molar of each species versus, for example, 0.2 molar of each species, right? There's simply less of each species to neutralize anything added. Yeah? That makes sense? So that's where my buffer capacity is how much of each species is actually present. Okay? All right, so let's go ahead and do some practice with this, right? So here we have this, right? Note these are important to take note of, right? Because we're going to use those. All right, so it says to calculate the pH of a buffer composed of 0.12 molar benzoic acid and 0.2 molar sodium benzoate. So even if you weren't really sure what benzoic acid was, which is fine, right? We know that benzoic acid, right? And I know that this is a buffer because the question tells me so, right? I know that this is a weak acid system, right? Here's my acid, here's its conjugate base. And look, the naming is just like we learned in like sophomore year, right? Benzoic acid comes from the benzoate ion, right? Naming rules, beautiful. Okay, so thinking back, right? I know I have my HA, plus my H2O is going to give me, and it doesn't tell you here, but it is a monoprotic acid, gives us our H3O plus my A minus, right? So then my K expression, by the way, what do we need to solve this problem? Right, we need the K value, right? And the K value for this happens to be, well, we'll write that down in a second. We have our H3O plus times A minus over HA, and this is going to equal 6.3 times 10 to the negative fifth, okay? So we have all of that, and I want to calculate the pH of this system, right? So here is where, and it depends on how you want to fill this out, right? But I think when we're talking about a buffer, it's easiest to go ahead and rearrange this, kind of like we talked about on the previous page, where I have Ka times HA over A minus is equal to my H3O plus. Okay, so then when I solve for this, right, I'm just going to take my 6.3 E negative 5 times my HA in concentration. So HA is the protonated acid form, so 0.12 over my base form, which is 0.2, right? And that's going to give me my H3O plus concentration, yes? And then how do I take that to my pH? Right, I'll just take the negative log of that once I get that answer. Yes, does that make sense? Okay, next up. All right, so we want to calculate the concentration of sodium benzoate. So which form is sodium benzoate? Right, that's my A minus. That must be present in a 0.2 molar solution of benzoic acid to produce a pH of 4. So if I know that I have a pH of 4, right, that means 10 to the negative 4, right, which is 10 to the negative, I don't know why I wrote that. 10 to the negative 4 is the molarity of my hydronium ion, right? So I know that on the front end. I also know the concentration of this. I also know my pKa. So here, right, we could set this up again, all right? And then we have all these pieces. So let's just go ahead and plug it in, right? So we know 6.3 times 10 to the negative 5th. And then we know our HA is 0.2 molar. This is the piece we don't know. And we know H3O plus is 10 to the negative 4th. And then we're just going to solve for our A minus. Yes, makes sense? All right, make sure you can do these. And in the next one, we start talking about what happens or how to do the calculation when we add a little bit of strong acid or strong base to a buffer system. All right, thank you for listening. Be good, and I will see you guys soon. Bye.